Okay, the Simmons-Smith reaction in carbenoids. So I think we're going to do something here that makes a lot, the chemistry we're going to do here makes a lot of sense. We're going to have to deal with some weird words and a couple more name reactions, Simmons-Smith and carbenoids, but hang tight, be patient with yourself, and we'll look for some similarities, make it easy to memorize, okay? So first of all, organozinc. All right, now organozinc compounds. So what have we done before? We did organolithium compounds, organomagnesium compounds, which had a halide on them, organocopper compounds, which had a lithium here and two organos, right? So we did lithium, magnesium, and copper, and now we're doing organozinc reactions. In the organozinc, which of these do they look like? Can you see? I'm going to argue that they look like Grignards, right? So we're going to do organozinc. Wait, how do you spell X? Spell it with an X. Just a second here. X. Organozinc compounds. And copper and zinc are way down the periodic table. These are over to the left, right? So this is going to be, these are going to be treated like this. Minus. Minus. This, we sort of figured stuff out by treating it like that, but it's not nearly as polar. And the same thing goes for zinc, right? Carbon-zinc bond is not nearly as polar. Let me do a highlighter. I should go back and forth. That would excite things. You guys would love that, wouldn't you? Look at this. Because the carbon-zinc bond is not nearly as polar as the magnesium bond, organozinc compounds give the carbon atom a partial negative character, but not much ionic. Okay? Back to the pen. That was great, wasn't it? Nice highlighter. All right, so the Simmons-Smith cyclopropionation. Can you guess what we're going to be making with cyclopropionation reactions? Yes, cyclopropane. The Simmons-Smith cyclopropionation utilizes an organozinc compound, which has got a couple iodines on it, and it's just a beast, okay? Actually, this looks like methane, doesn't it? Can you see methane here with a couple I's? So this is diiodo, methane, right? You treat this with, I don't know, that needs to be memorized, I guess. A zinc-copper couple. A zinc-copper couple in diethyl ether, and you get something that looks like, watch this. Right? Remember Grignard? Okay, and there we go. Okay, now it's got this other iodine on it. Yes, that's true. But if you can see the similarities, perhaps this will help you memorize it. So it's called, I guess, iodomethyl zinc iodide. Okay. Well, I don't think I'm going to call it that unless I'm reading it, because there's no way I'm going to remember that. So the zinc copper is a zinc copper couple that forms from zinc dust. We don't really know about it, so let's skip it. Yeah, we're making that stuff, and really what we're making, you see what we're making here, right? We're making something that looks like Grignard, and you've done that before, so there's going to be some similarities. The difference is it's not as polar. All right, now in the Simmons-Smith cyclopropionation, we take this copper zinc stuff, which looks like R and a metal, right? And a halide, which also looks like magnesium bromide, right? There's our Grignard. So here's another form of that with an iodine on the other side. It acts both as a nucleophile and an electrophile. This is weird. Well, actually, we've seen this before, right? We've seen this with borane, and we saw it with mercury that we used, mercury 2 acetate. Remember that? And when we were making alcohols. So where you had something that was both the electrophile and the nucleophile. This has to be memorized. So a lot of times you're able to recognize what a nucleophile and electrophile is. This one I don't think so. I don't think so. I mean, I guess you've seen pi bonds act as nucleophiles before, and you've seen lone pairs of electrons. Whoa. Lone pairs of electrons act as nucleophiles. So yeah, you've seen that before, but it's not obvious when you're looking at the. I don't think it is. Okay, and then this other iodide comes over here. Boom, and that has to be memorized. ugly arrows. Sorry for the ugly arrows. All right, so you see what I made? Cyclopropane. Boom. Now, since this is all done, you've got this atom and it's on the same side of this double bond, you know that this is going to be stereospecific. Time for highlighter. Stereospecific, right? Because it's all happening on this side of that double bond. All right, so if these are E, these are both going to be out in front or behind. Depends on which side this comes in on, right? But they're going to be on the same side. Syn. All right, let's look at another one. Now, cyclopropanation. Other cyclopropanation reactions can be achieved. I think this is the last slide. Other cyclopropanation reactions can also be achieved by using a carbene. And a carbene is this, right? Notice there's no formal charge on this. No formal charge, right? And it's trigonoplanar. Okay, that makes it an excellent electrophile. Great target for a pair of electrons. And there's the electrons right there. Wham, right? Now, once those guys go in there and make a new bond with that, these electrons are a good nucleophile, right? So this is also an electrophile and a nucleophile. Both an electrophile, yes, and a nucleophile. Yes. Specifically, these electrons are the nucleophile, and the nucleus is the electrophile. Right? Let me say that again. The electrons are the nucleophile, and the nucleus is... said that backwards, sorry. Start again. The electrons are the nucleophile, and the nucleus is the electrophile. Okay, of course. All right. So carbene's incomplete octet is the reason it's reactive. So we have two sort of carbenes. One's called a carbenoid, and the carbenoid was that zinc, right? Which we've said a couple times now. Oops, crud! I don't like using this eraser because I'm always afraid I'm going to erase or boom. Okay, let's go back here. Pen. This we've said before. I've said it several times here right now. That looks kind of like a Grignard. Very similar to Grignard and different, right? Because it's not as polar. Okay, hope that's helpful. Best wishes with carbenoids and cyclopropanation.